So we have defined resistance to be equal to the ratio of potential difference over current. Well, different materials behave differently when an applied potential difference is given across them. It's important for us to know and to work with different types of resistors. The most common type of resistor that we're going to deal with in this class is the ohmic resistor. And an ohmic resistor has the behavior that when the resistance of that resistor an ohmic resistor has the property that its resistance is independent of the voltage and current changes. So what that means is if we have how we have graphed here, a graph of potential difference versus current, the potential difference versus current is linear. In other words, for a particular change in potential difference, we will have the same change in current. And if you were to measure the slope of this linear line, that slope would be equal to the reciprocal of the resistance. So we often rearrange this relationship and call it Ohm's Law. Ohm's Law says that the product of current and resistance is equal to the change of potential for ohmic resistors. And again, for ohmic resistors, the change of potential and current is a linear relationship where, look at here, R is the slope of the line in a V voltage versus current graph, while if we reverse that, if we do a current versus voltage graph, R is the reciprocal slope. I can't spell reciprocal right now. Reciprocal slope. Now, non-ohmic materials are those materials where the resistance varies as a function of current and or voltage. So the resistance at a point in a current versus potential difference graph, now the slope of the tangent line at a point in a current versus potential difference graph represents the resistance of your material at that point. So if we have a graph that represents some non-ohmic material that looks like this, we would see that the resistance varies with potential difference. When we have a small potential difference here, notice we have a small slope of the line. And remember that small slope of the line corresponds to a large resistance, because in this graph, resistance is equal to the reciprocal of the slope, which means that in this graph, as potential difference increases, the resistance decreases because the slope gets bigger. And as our potential difference continues to increase, the resistance continues to decrease because the slope gets larger. So this is a situation illustrating a non-ohmic resistor because the resistance varies as the potential difference varies. While with ohmic resistors, you could vary the potential difference, but the resistance will remain constant. Here are some plots of different types of materials. The plot A represents current as a function of potential difference for tungsten wire at constant temperature. The resistance is the same for any value of delta V on the graph, so we can say that that tungsten wire represents an ohmic conductor. Now the graph in the middle represents a gas in a fluorescent light, and this is clearly non-ohmic since the current versus potential difference graph is not linear. In other words, resistance changes as a function of potential difference. And for C represents a diode, which is a semiconductor device. And this diode is non-ohmic since, once again, current versus potential difference is not linear. So this brings us to discuss the different types of materials that we'll encounter in our class. We're primarily going to deal with metals. Metals are materials that have loosely bound electrons that are bound to the material, but not to any particular atom. So when a conductor is heated, its resistance goes up, and that's true of metals. If you heat metal, its resistance to the flow of current increases. Whereas semiconductors are materials that have actually relatively few conduction electrons, but can become conductors when they are doped with other atoms that contribute free electrons. So doping means you're adding a little bit of impurity to increase one of the properties that you desire. So the thing about semiconductors is when a semiconductor is heated up, its resistance actually goes down. And that's because resistance is a measure of potential difference per current, or at least that's how we defined it, potential difference per current. And so when you heat up a semiconductor, it actually releases few more conduction electrons. And those conduction electrons increase the potential difference. Those conduction electrons increase the current in your semiconductor. And if the current in your semiconductor goes up, your resistance goes down for a given potential difference. So that's a property of semiconductors. Now, superconductors is the holy grail of material science. Superconductors are materials that lose all electrical resistance at low temperatures, and this is due to quantum effects. Now, the reason for this is since charge carriers are moving in a frictionless environment, so with semiconductors, since charge carriers are moving in a frictionless environment, charge will continue to move through a semiconductor without the presence of an electric field. So once you get that current moving, it'll continue to move. You don't need to maintain that potential difference because there's no resistance for the current to overcome. Now, the reason why this is such a holy grail of material science is, wouldn't it be great if we could have semiconductors at room temperature? Right now, I'm preparing this lecture on my laptop, and my laptop is getting very hot in my lap as I'm dictating right now. And the reason why it's getting hotter and hotter is because of the electrical resistance in the circuitry in this laptop. And as this laptop gets hotter, it becomes less efficient. It consumes more power. And right now, I'm draining my battery at a very large rate. If this laptop could somehow be made of a superconducting material at room temperature, my battery would last an extremely long amount of time. That would be phenomenal. in regards to energy for our planet.